Hi, I'm Todd. In this section, you'll learn strategies for solving polynomial and rational inequalities. Let's begin by reviewing the objectives. Polynomial inequalities and rational inequalities. Now, we can solve a polynomial inequality by getting 0 on one side and looking for where the graph is either above or below the x-axis. Where the graph of the function is above the x-axis, that's where the polynomial is positive. And where the graph is below the x-axis, that's where the function is negative. Let's take a look at an example. Here we have x cubed plus x minus 3 less than 3x squared. So what we're going to do is move the 3x squared to the left-hand side by subtracting 3x squared from both sides. And that'll give us x cubed plus, let's see, I'm going to make that a minus, x cubed minus 3x squared plus x minus 3 less than 0. So now that I have 0 on one side, I'll solve this by graphing the left-hand side and looking for where the graph is below the x-axis. And I'm interested in where it's below because this is a less than. So I'll do this on my graphing calculator, turn it on, and under the y equals menu, I'm going to enter x cubed minus 3x squared plus x minus 3. And I think we'll just graph this in a standard viewing screen. So if we use Zoom standard, this should give us a nice graph. And there's a graph of the polynomial. Now what I need to do is I need to find the place where the graph of the polynomial crosses the x-axis, or the x-intercept. And we can use this by using a feature in the calculator, which is the 0 feature. And remember, the x-intercept is also called the 0 of the function. So I'll select 0. And now that calculator is asking me for a value for the left bound. So I just need to make sure I select a value that's clearly to the left of where I think the 0 is. So I'll select that point there. And now I need a right bound, so I'll move it over here somewhere to the right of where I think the 0 is and press enter. And now it's asking me to guess, so I'll move it to right about where I think that solution is, or that 0 is. It's right about there, so press enter. And it gives me the 0 of 3. Now, since we are trying to solve an inequality, a less than, we're interested in where the graph is below the x-axis. And this graph is below the x-axis for x's to the left of 3. And so I know the solution is the interval from negative infinity to 3. Now, I need to make it open on the left side because we certainly can't include negative infinity in our interval. So I wouldn't want to make this a closed interval. I'm going to make it open. And it's also open on this side because this is strictly less than. There's no equal sign here. If this were a less than or equal to, then I'd want to close that in. But in this case, I certainly don't want to do that because 3 is not part of the solution set. Well, let's go through a process that we can use for solving polynomial inequalities. The first step in solving a polynomial inequality is, if necessary, write the inequality as p of x less than 0, where p of x is a polynomial and less than may be replaced by greater than, less than, or equal to, or greater than or equal to. The second step is to solve the equation p of x equals 0, either symbolically or graphically. The solutions are called boundary numbers, or boundary values. The third step is to use the boundary numbers to separate the real number line into intervals. On each interval, p of x is either always positive or always negative. To solve the inequality, either make a table of test values for p of x or use a graph of p of x. The solution set for p of x less than 0 corresponds to intervals where test values result in negative outputs, or to intervals where the graph of p of x is below the x-axis. Well, those are some pretty extensive steps, so maybe we better see how to do this with an example. Here we're asked to solve the inequality x cubed greater than or equal to 2x squared plus 3x, symbolically and then graphically. So we'll start out symbolically first. Now notice that we don't have a 0 on either side of this inequality. So my first step is to get a 0 on one side or another. So I'm going to subtract these two terms and move them to the left side. So that'll give me x cubed, let's see, x cubed minus 2x squared minus 3x, and that's greater than or equal to 0. Now the next thing we need to do is set the left-hand side, the polynomial on the left-hand side, equal to 0. So that's x cubed minus 2x squared minus 3x equal to 0. And we need to solve this equation. Well, remember, the first step here is to look for any common factors. X is a common factor, so the first thing I'll do is factor out an x. And that leaves me with x times x squared minus 2x minus 3. And that's equal to 0. Now this polynomial, x squared minus 2x minus 3, we can factor. And that's equal to x times x minus 3 times x plus 1. And that whole thing's equal to 0. So what we see here are the solutions are x equals 0 or x equal 3 or x equal negative 1. And so the intervals we have to check are negative infinity to negative 1, negative 1 to 0, 0 to 3, and 3 to infinity. So I've started a little table here, and I have the intervals I need to check here. And on each of these intervals, I've selected a test value that I'm going to check in the polynomial. And I can check these values. And what we're really interested in here anyway is just the sign of the polynomial for those test values. And if I enter the function into my calculator, I can quickly test whether or not the polynomial is positive or negative. So I'm going to enter this polynomial into my calculator under y1. We have x cubed minus 2x squared minus 3x. And I'm going to just look at the table. What I want to do, though, is under table set, I want to make sure that I have this independent variable set to ask, because I want to be able to type in each of these x values as I go. And so it's set to ask. I'm going to go second graph now, which takes me to the table. And now what I can do is type in each of my test values. The first one's negative 2, so that gives me a y value of negative 10. So I'll record that over here on my table. And that tells me that the polynomial for that test value was negative. Next we'll check negative 0.5. So I go back to my calculator and I input negative 0.5 for x. And the y value that corresponds to that x value is 0.875. So we have 0.875. And I'm really interested in the fact that that's positive. We'll check 1 next. So I go back to my table and I enter 1 on the calculator, press enter, and we get negative 4. And that's negative. And finally, we'll check 4, and that gives me 20, so that's positive. Now, the polynomial we're trying to solve is greater than or equal to 0. So we're interested in the intervals where the polynomial is positive. So on our table, we see that polynomial is positive from negative 1 to 0 and from 3 to infinity. Now, it's also important to realize that we have to use closed intervals, because in this case we have an inequality that is greater than or equal to. So this interval will be closed from negative 1 to 0, and union the interval from 3 to infinity. This one's half open. It's closed on the left because 3 is included in the solution set. We can never reach infinity, so we never want to use a closed interval with infinity on that end. Okay, we were also asked to solve this polynomial inequality graphically, so we'll do that now. Now I've already got this one entered into my calculator under y1, so if I just press graph, it should draw the graph, and there's the graph. What I need to do now is to find these zeros, or these x-intercepts. And remember, the solution set are the intervals where the graph is above the x-axis. And in this case, it's also equal to the places where it crosses, since we have a greater than or equal to. So we'll use the 0 function on the calculator. We'll find this one on the left first, so I need a left bound. That looks like it's far enough to the left. and then we need a point on the right, and then a guess. And so it tells me that 0 is -1. And that's good because it corresponds with the one of the solutions that we got. We'll go back here and find this other 0 now. So I need a right value. There it is. Or that was a left value. I need a right value next. Then if I press enter, it gives me 0. That's also the same as what we got. And now we'll try to find this last 0. Need a left bound. That should work. And whoops, went off the screen. There's a right value, and it gives me 3. So we can see now that the graph also verifies the solution that we got symbolically. Now, in that last example, we solved a polynomial inequality. And next, we're going to solve rational inequalities. And the process is somewhat similar. The first step, if necessary, write the inequality in the form p of x divided by q of x greater than 0, where p of x and q of x are polynomials. Note that greater than may be replaced by less than, greater than or equal to, or less than or equal to. Solve the equations p of x equals 0 and q of x equals 0. The solutions are boundary numbers. The next step is to use the boundary numbers to separate the real number line into intervals. On each interval, p of x divided by q of x is either always positive or always negative. Use the table of test values to solve the inequality in step 1. So we'll take a look at an example. Here we're asked to solve the rational inequality 1 divided by x minus 3 less than or equal to 5 divided by x minus 3. So the first step is to get a 0 on one side of the inequality. So I'll subtract 5 divided by x minus 3 from both sides. We have 1 divided by x minus 3 minus 5 divided by x minus 3 less than or equal to 0. I need to combine these two rational expressions together. So they already have common denominators. I just need to subtract the numerator. That'll give me -4 divided by x minus 3, and that's less than or equal to 0. Now we need to find the zeros, or the x values that make the numerator and the denominator 0. -4 is a polynomial, but -4 can never be 0, so we don't have to worry about that. We do have to find the x values that make x minus 3 0. So if I set x minus 3 equal to 0 and add 3 to both sides, then we find x equal 3 is a solution. And so in this case, we only have two intervals to check. The interval from -infinity to 3 and the interval from 3 to +infinity. So I've set up a table, and in this table I have the intervals we need to check, and I've selected a test value from each of the intervals. Now again, we need to find the value of the rational function for each of these values. So I'm going to go ahead and input this function into my calculator under y1, and we have -4 divided by the quantity x minus 3. And again, I'll use the table feature in the calculator, and I want to delete these out because those were from the previous example. And we want to check the first test value, which is 1, and that value is 2. So the value of the rational function is 2, and that gives us a positive value for the rational function. Now, we'll check 4. 4 gives us -4. And that means the rational function was negative. All right, so we were trying to find where the rational function was less than or equal to 0. So we want to know on what interval it was negative. Now this is a less than or equal to, but remember, x equal 3 makes the denominator of the rational function 0, so we still have to include it. So the solution in this case is going to be the open interval from 3 to infinity. Okay, I'd like you to try this next example. And in this example, you're asked to solve the following rational inequality. X plus 1 divided by x minus 2 less than x plus 3 divided by 2 minus x. So stop the tape and try this. Okay, now I'll give it a try. First thing we need to do here is get a 0 on one side of the inequality. So I'll subtract x plus 3 divided by 2 minus x from both sides. that gives me x plus 1 divided by x minus 2 minus x plus 3 divided by 2 minus x less than 0. Now, I need to do something with these denominators. Here I have x minus 2, here I have 2 minus x. If I factor out a negative, reorder those, so I have x minus 2, make that positive, that should do the trick. So we'll have x plus 1 divided by x minus 2 plus x plus 3 divided by x minus 2 is less than 0. And now I have common denominators, so I can combine the numerators. X plus x is 2x, 1 plus 3 is 4. So we get 2x plus 4 divided by x minus 2 less than 0. So the next thing I have to do is check when the numerator and the denominator are equal to 0. So the equations I have to solve are 2x plus 4 equals 0, or x minus 2 equals 0. So in this case, well, one step I can do is divide or multiply both sides by a half. There's a common factor of 2 there. That'll kind of simplify things. So that would give me x plus 2 equals 0. And then if I subtract 2 from both sides, I get x equal negative 2. On this side, I need to add 2 to both sides, so that would give me x equal 2. So now the intervals I need to check are the interval from negative infinity to negative 2, the interval from negative 2 to 2, and the interval from 2 to infinity. Okay, so we'll set up a table. Here I have the intervals I need to check. I picked a test value from each of the intervals. And again, I'll use the calculator to test these values. So I need to input the rational function under y1. And the numerator is 2x plus 4 divided by x minus 2. And be sure to include these parentheses. Now we'll go back and look at the table and input these x values. The first x value I need to check is negative 3. So I'll input negative 3 for x, and that gives me a y value of 0.4. And that's positive, so that tells me the rational function is positive on that interval. The next one we need to check is 0. That gives me negative 2. It tells me the rational function is negative on that interval. Finally, we need to check 3. That gives us 10, so we know the rational function is positive on that interval. Now, the inequality that we were solving was a less than, and so we need to find the intervals on which the rational function is less than 0. And that would be right here where it's negative. Furthermore, this was a strict inequality, so neither of the endpoints or boundary numbers for the interval will be included. And so the solution set is the interval from negative 2 to 2. Now let's see if we can check this solution using our graphing calculator. I've already entered the function under y1, so all I need to do is press graph. And here's the graph. And remember, we're looking for the interval where the rational function is negative, so that's where the graph is below the x-axis. So notice I have one place where the graph crosses the x-axis, and then I have another place where the function's undefined. Now this function we know is undefined at positive 2. So I need to go and find that 0 now, and I can do that on the calculator using the calculate feature and choosing 0. I need to give it a left boundary, so I'll move my cursor over here to the left, select that point. Now I need a right boundary, so I'll move it over to the right, select that point, and a guess, oh, that'll work. And it gives me a 0 of negative 2 there. So we can see the graph is below the x-axis from x equal negative 2 to 2, and so this verifies that our solution set is the open interval from negative 2 to 2. Well, in this section, you've learned how to solve polynomial inequalities and rational inequalities. Be sure to do some examples out of your textbook so you can solidify these concepts, and I'll see you next time.